Good morning, everyone. Myself, Sridhara. So, again, after the completion of the functions, today we are trying to focus on a specialized function known as recursion and how it was implemented. So, that's why the topic and the title for the today's class is recursion and implementation of functions. If you observe the figure in this slide, where it was a little bit meaningful, and in a nutshell it is trying to show the core point of recursion. In that image, if you look at the extreme left image, which was a little bit bigger in size, then slowly moving to the right side of it, it is the same picture with a little bit lesser size. And if you move a little bit towards right, then once again the same figure with a reduced size, and so on. So what this particular picture speaks and how it was related to recursion is nothing but dividing a complex problem and finding its solution by reducing the size of the problem. Hope I was clear, but once again let me repeat. So recursion is a sort of process where a complex problem was divided into subproblems such that we can find a solution. Instead of finding the solution for a complex problem at a larger size, let us try to reduce the size of the problem, and then we can find out the solution. Good. So if we keep on moving to the next parts, slowly we can understand what exactly. But before to that, I mind you, recursion is such an important topic, and even at the time of the problem solving also, this recursion plays a very important role. So please pay special attention, and to get a mastery on the recursion, first let us try to understand the science behind it. Then we can easily understand what the recursion will do. Good. Now let's move on to the next one. Initially, let us try to understand what is a formal definition for a recursion or a recursive function, because ultimately recursion is a process and we are implementing it with the help of the functions. So that's why in our discussion recursion and recursive functions are used a little bit interchangeably. So what exactly you mean by recursive function is a function that calls itself. A function calling itself. So in our previous discussions, especially about the functions, there categorically we discussed about two different functions. One is the calling function and the second one is called function. I repeat again. In the regular implementation of a function, we use it to have the two type of the functions. One, the which is calling function, and the second one is called function. So let me make it a little bit simple. Suppose I am going to call my friend Prasad, hi Prasad, like that, or over through a telephone. Because I am calling my friend Prasad, then I will be called as calling person. I'm going to call him. I'm going to call him. Hey Prasad. So then I will be the calling person. Now on the opposite side, where Mr. Prasad is there, he was called by me. So that's why he is known as called person. Okay. Or let me say that there is a person with name, say some particular A. There is a person with the name A, and he is going to call the person, say some particular B. So now this A is calling and this particular B is called. So calling person and called person. Similarly like that, calling function and called function. So in a nutshell, let us say that a recursive function is a function that calls itself, whether directly or indirectly. Then coming to the second point, each recursive call is made with a new independent set of arguments. So here please make a note that recursion is a continuous process. Recursion is a continuous process. It may be called for one time, two times, n times, etc. So it keeps on rotating. So that's why each recursive call is made with a new and independent set of the arguments where the previous calls were suspended. When you are calling the recursive function for the third time, the second previous call were suspended. Mind you, and please make a note that I am going to use the vocabulary suspended. It was not cancelled. For the time being, it was into a hold. So the previous calls were suspended, and basically recursions were used to solve right from a simple programs to very complex programs. So in a summary, let me say that recursive function is a function that calls itself. Means a little bit technically, if the calling function and called function were the same, just you call it as recursion. And now let us try to understand this particular recursion and recursive procedures in a little bit deeper way. As per that, again, recursion is a way of defining a concept where the text of the definition refers to the concept that is being defined. That's in general. But coming to the programming, you please focus here. In programming, a recursive procedure is a procedure which calls itself. Okay, and mind you, the most important is here you had a caveat. Look at this. The recursive procedure call must use a different argument. You must use a different argument than that of the original one. Suppose if your original argument is n, when you call the recursive function for the first time, and for the second time the argument must differ. So for the first time the argument was n, and for the second time the argument was n minus 1, and for the third time for the same recursive function the argument may be n minus 2. Likewise, the recursive procedure call must use a different argument than the original one. Otherwise what happens, you know, it gets into an infinite loop. Okay, if you are little bit in dilemma about what exactly it was, now you look at here at the bottom of your particular screen. I am going to present a function. Now please look at this. So here this is a function, call it as f of n. This is the function f of n. Now n is the argument. Mind you, n is the argument. This is the argument. But initially, when I am calling this particular function, the argument is n. But the same function is once again called here. Look at this, f. But this time, the argument is n minus 1. That's what I specified here previously. That is the recursive procedure. Please look at where my pointer is going to be. So the recursive procedure call must use a different argument than that of the original one. Otherwise, the procedure would always get into an infinite loop. Suppose here the calling is n, and once again here I am also going to call by mistake it as n, then it can be into an infinite loop. Your recursive function cannot be breaked at one point of time. Of course, recursion is a continuation. Recursion is a repetition. But that repetition should come to an end. Unless and otherwise, it becomes an infinite loop. And if I want to end at one point of time, the size of the problem or the argument that you are passing to the function must be reduced. Clear? So till now, focusly, mind you 2 points. First one, recursion is a function that is calling itself. Then, recursion is a procedure used to solve the complex problems by reducing the size of the problem. Let me say in this particular formula, n is my size of the problem. Somewhere it may be x, somewhere it may be y. And now I am going to reduce it by using n minus 1, because ultimately my n value should reach to 1. Okay. So now for the same thing, for the same procedure what I have explained so far, let me try to give a little bit easier example, and that is very synonymous to this recursion, is finding the factorial of a given number. Got it? The recursion best example you can easily understand is finding the factorial of a number. Suppose I want to find the factorial of the 5. Mind you, I want to find the factorial of the 5. So let me write it here. Say for example, I want to find factorial of n, where n is the size of the problem, and I am going to say that it was factorial of 5. 5 is the size of the problem. 5 is the size of the problem. But now the thing is, I can find the factorial of the 5 as 5 into 4 into 3 into 2 into 1. 5 factorial is mathematically expressed as 5 into 4 into 3 into 2 into 1. So initially I want to find the factorial of 5. The size of the problem is 5, but I am going to reduce the size. Instead of finding the factorial 5, I would like to find the factorial of the 4. Got it? Similarly, when I want to find the factorial of the 4, where 4 is the size of the problem, I want to find the factorial of the 3. I am reducing the size of the problem from 5 to 4 to 3, 2 and 1, because finally the factorial of the 1 is 1. So that's why here it is a classic example about saying that what this particular thing is. The classic example is, it is a finding the factorial, and this is the mathematical expression. Is it clear? So now look at here. Factorial of a number f of n is equals to 1. Otherwise, it is n into f of n minus 1. So for the first time when I am going to call, this is nothing but the size of the problem n. But when I am going to call it for the second time, I am going to call this particular size as n minus 1. So that's the philosophy or the science behind this particular recursion, where the size of the problem is reduced. Good. Moving to the next one. We are trying to learn what this particular formula that I previously mentioned means. What is the mathematical formula that our assumption that we are going to use to find the factorial of a number. Here we are going to repeat it the same. F of n is equals to 1 if n is 0. Otherwise, it is nothing but n into f of n minus 1. So this is the mathematical intuition behind this particular finding the factorial. I repeat once again. So you are going to calculate the factorial of n. Now the question is, what is the value of n? If the value of the n is given as 0, then its factorial is 1. If the value of n is 0, its factorial is 1. Otherwise, that's what we are going to express it with the help of else. Suppose let me say that n is not equals to 0. That's what do you mean by else? If n is equals to 0, your factorial is 1, agreed. Else means if the value of the n is other than 0, then what it is? N into factorial of n minus 1. The same thing we are trying to give it with the help of a C function, where the name of the function is say some particular factorial, and I am going to pass a parameter. Of course, I am going to pass an integer parameter. That's nothing but n. And finally, at last, after the successful completion of this factorial function, the function is going to return an integer value. So luckily here in this example, the name of the function is factorial. It is argument is an integer and its return value is also an integer. Okay, yeah. Now coming to this particular condition, if n is equals to 0, means if the value of the n is equals to 0, what I am trying to return is 1, means the factorial is 1. Otherwise means else, then what I am going to call it as n into factorial of n minus 1. Simple. And if you are able to understand it, it's quite easy. Okay, so let me come back once again so that easily you can understand. Now let us move a little bit technically. I'm trying to find out the factorial of a given number in C language, and this is the code related to this. The name of the function is factorial. The argument that it was passing is say some particular integer n, and after at the last it will return an integer value. So now for the time being, assume that this particular code was not there. What I am going to encircle it, assume that I didn't write this code. Then what will happen? It is going to happen that I am going to return n into n minus 1. So now let me say that the value of n is 3. For easy understanding, let me say that the value of n is 3. The value that I am going to use it is 3, and then it is nothing but n minus 1 is 2. Then the value of n will be 2, and value of n minus 1 will be 1. Then the value of n will be 1, and the value of n minus 1 will be 0. Then once again it will be 0, and where it's n minus 1 is minus 1. Then it is minus 1, n minus 1 is minus 2. It keeps on going. It keeps on continuing, which is an infinite loop. Which is an infinite loop. For example, if for n value is 7, when n is 7, n minus 1 is 6. When n is 6, n minus 1 is 5. So the value of n progresses like the value of the n is moved like 7, 6, 5, 4, 3, 2, 1, 0, minus 1, minus 2, minus 3, minus 4, and on and on and on, which is going to form an infinite. So that's why, no. I don't want to do it for an infinite number of times. I want to do it for a finite number of times or a limited number of times. So that's why, most importantly, the thing is, instead of having an infinite loop or a continuous loop, here we are going to specify a base condition. n is equals to 0. N is equals to 0, we are going to call this particular condition as base case. So this is the condition where your recursion stops. It won't move further. Let me say that n value is 5. 5, 4, 3, 2. After 2 your n is 1, and after 1 n is 0, and after this particular 0, when your value of n is 0, I am trying to break it. Mind you, there is no recursion in this particular part. If you observe it seriously, there is no recursion in this particular part. At the base case, there won't be any recursion. At the base case, you don't have any recursion. This is altogether what I am going to call it as base case. If n is equals to 0, I am not going to further call this particular factorial. If n is equals to 0, that's the end where I want to stop it, where I want to stop the recursion, and just I am going to return a value. Hope I was clear. And whenever I say that the n value is not equals to 0, means the value of n may be something. The value of n may be 5 or something else. Then what will happen it is, so here we are going to say that the n value is 5, sorry, the n value is 5, and there I am going to say that factorial of the 4, n minus 1 is 4. And again your n is 4 and factorial of n minus 1 is 3. And when your n is 3, factorial of n minus 1 is 2. And when n is 2, factorial of n minus 1 is 1. And when n value is 1, your factorial of n minus 1 is 0. Now you are arriving at this case, because your recursion keeps on rotating, keeps on moving until your value of n is 5, 4, 3, 2, 1. And the value of n reaches to 0, it automatically comes to a base case. With this particular base case, there was no recursion. We are stopping the recursion. Otherwise, it keeps on rotating. Hope you are able to understand this. So this is, now look at this carefully for 1 minute. This is what all together, this is what it was. So you should have a base case. Every recursive function should have a base case. What happens if I write a recursive function without a base case, without a termination case? Then it can become an infinite loop. It becomes an infinite loop. That's why every recursive function must have a base case. Okay, let's move to the next one. And this is a little bit an important theoretical concept. Sir, as you are going to say that recursion is a sort of repetition. Similarly, iteration is also a sort of repetition. Means whenever you are using the loops like for, while and do while, they also keep rotating, they also keep continuous. Then when there is an iteration to repeat and when there is a recursion to repeat, what makes the difference? What makes the difference between recursion and iteration? That's what we are going to discuss here. But before to that, very seriously I mind you, if you are writing a recursive function, inside of that function don't use iteration, don't use a loop. And when you are writing a loop, inside of a loop you don't write a recursion. So finally what the takeaway point is, recursion and loop are complementary to each other. They are complementary to each other. If you write a recursion, don't use a loop. If you use a loop, don't use a recursion. Both are opposite, complementary to each other. So here I am going to be a little bit more elaborate on this recursion versus iteration. Iteration can be used in place of recursion, but an iterative algorithm uses a looping construct and a recursive algorithm uses a branching structure. Please focus a little bit of time over here. An iterative algorithm uses a looping construct. a loop like a for or a while or a do while or something like that, where the iterations uses a looping constructs. But for a recursion, we don't use the loops, but we are going to use a branching structure. I think you can recollect that what is this particular branching structure. Branching structure means where I can use any sort of if condition or switch case conditions, decision making. That's what do you mean by branching structure. Is it clear? Then the second point is recursive solutions are often less efficient in terms of both time and space than that of the iterative solutions. Please read into this particular point a little bit critically. When you say that, sir, when recursive solutions are less efficient in terms of the time and memory or space, why we have to use that? No, 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 no. They were less efficient when compared to the iterative solutions. When there is a comparison made between an iteration and recursion, recursion is less efficient. But of course, there is a positive point for the recursion also. You look at this third point. Recursion can simplify the solution of a problem, often resulting in shorter, more easily understood source code that you can write. It's very simple, just made of only 2 to 3 lines, a very little less number of times. So better as a part of your interesting, you read the distinction between recursion and iteration in a clear-cut manner. Then contents of a recursive method, that's what we did it in the last time. If n is equals to 0, return 1, that is the base case. Got it? When you are writing a recursive function, and if I am writing a formula something like this, sorry, it was not visible. If I am writing something like this, if n is equals to 0, it is a base case, else n into factorial of n minus 1, that is the recursive case. Base case will terminate the recursion. Okay, whereas recursive calls will keep on calling again and again. So now this is where let us try to visualize the recursion. Is it clear? Huh. First of all, the thing is, I want to find the factorial of 4. I want to find the factorial of 4. But I'm going to make a recursive call that factorial of 3. Then once again, I am going to call it as recursion of 2. Then I am going to call it as recursion of 1. Then finally, I am going to land at recursive of 0. But mind you, this is the end. Here it was ended. There was no recursive factorial of 0 minus 1 is minus 1. No, 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 no. We are going to end this particular reducing the size of the problem with 0. That's why we are going to call it as base case. And this particular base case is going to return a value of 1. Then 1 is multiplied by 1, that gives 2. 2 multiplied by 1, 2. Then 3 multiplied by 2, 6. Then finally 6 multiplied by 4, 24 is your factorial. Got it? So let me show this particular one in a little bit animated way. So this is how it gets into by one more particular problem, Fibonacci series, where the nth Fibonacci number is the sum of the previous two Fibonacci numbers. The nth Fibonacci number is the sum of the previous two Fibonacci numbers. So here you see the first term or the first number in this particular Fibonacci series is 1. Then 0, 1. 0 plus 1 is 1. 1 plus 1 is 2. 2 plus 3 is 1 plus 2 is 3. 2 plus 3 is 5. 5 plus 3 is 8. 8 plus 3 is 13. So 13 plus 8 is 21 will be the next term. So Fibonacci series is nothing but nth term is nothing but it's a sum of the previous two terms. It's a last previous two terms. That's why Fibonacci series of n is equals to Fibonacci series of n minus 1 plus n minus 2. And now If you look at the first Fibonacci term, that is 0, and if you look at the second Fibonacci series, that was 1. Now, what will be the third term? Third term is nothing but the sum of the second term plus first term. That is nothing but 0 plus 1, 1. Then once again, 1 plus 1, 2. Then once again, 2 plus 1, 3. Then once again, 2 plus 3, 5, and on. So, the Fibonacci series is defined as its nth term is the sum of the previous two Fibonacci terms, once again, which will be implemented using recursion only. By using the recursion only, we will do that. So, here you see the same thing what I discussed. If n is equals to 2, Fibonacci series is 1. If n is equals to 1, Fibonacci series is 0. Otherwise, it is a sum of n minus 1 plus n minus 2. That much easy it was. So, indirectly, I want to find out the Fibonacci series of fourth term. Fourth time I want to. So, fourth time is nothing but the sum of the 3 plus 2. Second term is nothing but the sum of the first term plus 0th term. Of course, there was no 0th term. Fibonacci of 1 is 1. Fibonacci of 2 is Fibonacci of 1 is 0. Fibonacci of 2 is 1. 3 is nothing but 0 plus 1, 1. And then 1 plus 3 is this one. Yeah, the same thing. This is how I am trying to explain it in the form of a tree. So now the Fibonacci series is 4. It is nothing but n minus 1 and then n minus 2. Is it not? So n minus 1 is 3 and n minus 2 is 2. Again, this will come back to 3 is come back to 2 and then 1. And again, this will be in 2. So Fibonacci series of 1 is 0. Here you please observe it. And Fibonacci's second term is 1. And now 0 plus 1 is 3. And now these two terms will come back to here. That's how do we calculate. Okay. So similarly, let us go for one more example. Sum of the digits of a number using recursion. You please try to make a note of this code and try to debug yourself. I mean to say, you can do the hand simulation. You try to substitute the value of the number as 487. So here also I can tell you one more important point. Previously, we didn't focus much on there. Here I want to make it as a two partitions. Here it is the main function and here it is the sum function. So now main function is the calling function and sum is called function, because the function sum is called from the main function. That's why main is the calling function. Sum is called function. And you look at here. So the calling function is sum and the called function was also sum. So this comes to this recursion. Okay. So now you have to see this example into two parts. You look at this particular whole thing into two parts. What is the first part is this one on the left hand side, where the calling function is main and the called function is a sum. Whereas coming on to the right side, the calling function is sum agreed. But once again, you look at here, the called function was also the sum. When calling and called functions were both the same, then we are going to call it as recursion. Then we are going to name it as recursion. So what I suggest you is, you kindly make a note of this particular problem, or subsequently I will share this PPT with you. Now you try to evaluate yourself on it. Means substitute the value of the 487 here in this particular num. You substitute the value here, this particular num as 487. Sorry, I was a little bit poor in this. So now according to that, here you take care. At one time I am using runtime reminder operator, and at the second time I am using integer division operator. Both will function and behavior differ. According to that, you try to explain, you try to elaborate yourself. Anyhow, in the next class we will have a deeper look into this. But before to that, what I suggest you is you try to make a hand simulation for this particular code on your own. Take a white paper, substitute the value of the 487, then you take out what is 487 mod 10, then you take what is 487 divided by 10. Likewise, you try to evaluate yourself. Definitely, we will repeat this once again into the next class. And finally, I want to end this today's session with a beautiful example. Now, we were discussing about the recursion. As a part of the recursion, I gave you three examples. One is the factorial of a number. Second one is the Fibonacci series. And the third one is this is sum of the digits of a number. Now, if you recollect this Fibonacci series, where nth term is nothing but the sum of n minus 1 and n minus 2 terms, the same Fibonacci series was articulated or framed in such a beautiful manner. Given a staircase of n steps, maybe 2 steps, maybe 1 step, maybe 10 steps. And of course, you can climb only 1 or 2 steps at a given time. That's it. For these given n number of the steps, you can take only 1 step or you can take 2 steps. At a time, I am a very young and athlete and a long jumper. I want to take n by 2 steps at a time. No, no, no. We don't agree for that. The constraint in this problem is, mind you, the constraint in this problem is at a time you can either climb 1 or 2 steps. Now the task is to return the count, the number of distinct ways you can climb or you can go to the top. Got it? Suppose, for example, in my building, when I want to go from first floor to second floor, let me say in my apartments, when I want to go from first floor to second floor, I am supposed to climb 7 steps. And now you have to say me, in how many different ways I can go to the second floor. 1 step at a time or 2 steps at a time. Only the constraint is, at a time you can climb only 1 step or 2 steps. That's a mandatory. When I am having 7 steps, first I will take 3 steps, then again I will take 3 steps, and finally I will go with the 1 step. In the sense, that is a wrong solution. Absolutely, that was the wrong solution. You are violating the constraint. The constraint is you can climb only 1 or 2 steps at a given time. Now you tried it. I am going to open a secret. Before to solving this problem, better you try to revisit the Fibonacci series and try to understand the science and the philosophy behind it. Easily you can solve it. Hope we were a little bit clear with this recursion, what exactly it was. And we are going to use this particular recursion in many more ways and many more areas, like in the data structures, like in the trees, like in the sorting algorithms, and of course in searching algorithms also. The applications of recursion is very wide. You cannot number them like 1, 2 and then 5. N number of applications and n number of the cases you can use this recursion. Of course, we will discuss about the usage of the recursion at the time of the sorting, searching, trees, etc., in the due course of our syllabus. Got it? Thank you. Let me say that I want to end this. Thank you.